Yeah, thank you very much for the opportunity to present a project to you that we've been working on for the last 2 years and that I'm extremely proud of. I termed the presentation Connecting the Dots because of how we are actually combining different types of data to perform distribution state estimation. So that's a topic that probably you're aware is getting increasingly popular, and we actually implemented a distribution system state estimation demonstrated within this project, and I just wanted to share with you what we've learned and how far we've got with this project. So given the environment that the distribution system is currently in, with the change of customer behavior, the appearance of more flexible, high-powered DERs, obviously something needs to change about how the distribution network's being operated. So traditionally it was just planned for peak load, able to withstand any plausible peak load conditions, and that was it. I mean, with the advent of self-generation, additional relatively high power charging at home, battery systems, all these flexibilities on the customer side and the demand for the customer to be able to use it, the operational state of the network gets far more complex. I mean, there are a couple of initiatives targeting that, and I'm probably preaching to the choir. I just picked out on the one open energy networks because I think it's one of the broadest discussions, at least here in Australia, in trying to find out a way how to modernize and change the way distribution networks are being managed. They're going quite to the extreme in trying to establish and run the network effectively through a market. But what I really want to pick on is what you see in any initiative, not just here, is the need for additional network monitoring. And one concept that I really like about what they've done, operational envelopes. So operational envelopes don't pick too much on that specific term, and I think it's still evolving what you really understand, what people really understand when talking about operational envelope. But what I take from this is managing the capacity of a network. So being able to figure out what the maximum loadability of a network is at any given point in time, and offering that to customers as much as possible. And this is squarely where our project's been sitting. The primary focus is on the network monitoring, but not through additional data or how to do through additional measurements that will be installed, but just trying to work with what's already there to then support this capacity assessment, which in case of the open energy networks they call operational envelopes. We would probably call it a bit different, but that's just terminology. It's not about the conceptual thing. The conceptual thing is the same. So I would argue, and that was kind of the premise to start this project, is that most of the network operators, at least, or distribution network operators, at least on the MV level, probably already have enough data to perform distribution state estimation. On the low voltage, it looks a bit different, but we have a few possible answers to that as well. So I would argue that although it's not that everything within the network is being monitored and you don't have a measurement everywhere, you're actually swimming in a sea of data. Most network operators will have reasonably okay, if not slide formatting, they do have reasonably okay network models. They might not necessarily already be down to the point that you have ohms and capacitance values, but at least you have an asset register that gives you a reasonable understanding of what kind of cable has been used, how long it is. You would normally, somewhere within the network operator, have the switching state of the networks or the electrical topology. This is already reasonably okay. It's normally already good enough to come up with a basic network model. You usually also have information about your customer base, some statistics about it, like annual energy consumption, the type of customers you have at different load points. You do usually have a bit of measurement, at least. Some from SCADA, some do actually have dedicated measurement devices to monitor asset performance. And you might even have some forecasts externally available or locally within the in-house, within the company itself. So we have a range of different data types. Through comparing the different DNSPs, the availability of these data types is kind of varying. They come with a varying quality and, depending on what the situation is, with a varying degree of usefulness. What we really need is a process that integrates them and is able to kind of figure out the bigger picture of how they relate to each other, what they mean, and also being able to handle varying availability. So not all data is available all the time or at every DNSP, and also being able to kind of manage different quality levels. So if you have less quality data, you get less accurate results, but being able to kind of quantify that uncertainty in the results, that's really, really, really important, because that makes the process manageable. So that's the Solar Enablement Initiative, the project I was talking about, basically at a glance. Our objective was to demonstrate that the majority of DNSPs actually have enough data to set up a functional distribution state estimation on MV level. The project's coming to its end on 5th of December, so in 2 weeks' time. And we've basically, for the DNSPs who directly participated, demonstrated that they actually that it is functional. So what we would normally ingest into the system would be a network model of some kind. So it might already be one spelled out in SYNCAL. It might just be one based on a switching state in an asset register, where we kind of model the individual elements. We take in load statistics, usually the type of customers, because we are on an MV level with this project. We would just have the number of customers of different types at each distribution transformer, plus the annual energy consumption. That's usually the load statistics that we used within the project. You could use other values if you wanted to, but that's what we used, plus the measurements. And this is where we've selected for the measurements, because this is probably where the biggest diversity is, where we selected 3 DNSPs, or not just selected, they volunteered, let's say this way. I'm absolutely appreciative of that, for the different measurement schemes. So the project was actually reasonably large, not gigantic, but reasonably large for a university project. And we received support from the ENA and API. And we're currently kind of preparing to share that, the results, the project results, back to the wider industry through these bodies as well. The main cash contribution came from ARENA. I'm eternally thankful for that. And the network operators that volunteered to trial this technology and participate actively within this project were Energy Queensland, United Energy, and Test Networks. We had some minority partners here, Springfield. I'm not sure if you're aware of it. Springfield, a privately owned city, effectively, just in the vicinity of Brisbane. They were just extremely interested in this technology, what it might enable for the community in terms of energy services that they might be able to offer to their residents. And Oricon just giving a bit of a kind of consultancy customer perspective into the project. It was collaborative, and I see Gerard here. It was collaborative between the University of Queensland and Queensland University of Technology. The bulk of the work was more at the University of Queensland, but was really enjoyable working with the QET guys as well, because we just formed one team. We were just sitting in the same room all the time. So much appreciated. I hope we can do something similar again. But focusing on the 3 DNSPs that we selected, just for the different types of measurement that I had. With the, well, it's not absolutely clear cut. So there are a bit of overlaps, but in general, the way the 3 networks are kind of monitoring their performance and collecting measurement data is Energex has about 30% of its distribution transformer fleet equipped with smart meters, effectively. So smart meters in a weatherproof box with a 3G modem. So they would measure voltage, active, reactive power, and normally that would be averaged over 10 minutes and then basically communicated back to a central system every night. So we selected that because that's an interesting point. From an MV perspective, these are the load points, and we wanted to work with that. Energex also has some SCADA data being taken on the MV level itself in the substation. So we chose not to use it, just to keep it a clean case. Because in this case of Test Networks, who don't have much of this kind of downstream measurements within their networks, we had to basically mainly rely on SCADA data. So we tried to keep these 2 cases relatively clean. The kind of an interesting one was United Energy, Victoria, smart meters. So they had almost 100% coverage with smart meters, which is obviously in the LV network. So in the case of United Energy, they then provided aggregate measurements up to the distribution transformer as well as inputs into the system. So it spans quite a range of different measurement scenarios. You can mix and match if you have multiple ones of them. One of the ones I'm most proud of is actually test networks, because the measurement density is extremely low there. So what we see there is, I think, the Bridgewater feeder has 350 or so distribution transformers, and we solved it on 9 measurement points. So that was extremely challenging, but the results are not too bad. And it is, if you look under the bonnet of the results, you see just the value that comes from SCADA measurements, in this case mainly from voltage regulators and auto reclosers. So it's immense value in these measurements, that equipping them with modems and bringing that data back. That's, if I can kind of hammer in one message, that would probably be it. So we worked on all these 3 networks, and were able to demonstrate a functional process for all 3 of them. Just a snapshot here is part of the visualization that we've built, and it's just displaying the voltage profile and the currents within the entire MV system. So the state estimation ultimately, once it has run, it is as if you had run a power flow simulation. It reveals the most probable system state, and as a system state, it is the way it is represented, it is complete. So you can actually calculate each and every operational value. So you get from partial measurements plus network model plus some load statistics, you get full visibility of the system. Sure, there's still a degree of uncertainty about the system state, but this remaining uncertainty can usually be quantified, because the state estimation requires you to associate each input value with a level of uncertainty that it's in it, which we project onto the outputs. So all of the values that we calculate would come with an uncertainty value. Yeah, and as I said, it was functional on all 3 networks, irrespective of their measurement configuration. And what you get ultimately is complete visibility. So you get the solution for every branch, for every node, every operational value that you could possibly think of. And under the bonnet of this particular project is a state estimation that has been implemented on a 4-wire network model. So it was aiming at low voltage networks and being able to capture all the details that low voltage networks would normally require you to model. The idea was just low voltage networks are probably the most complex ones to model, and once you've done that, the rest becomes relatively easy. So although here we use it on the MV, for the distribution transformers you get the LV side as well in 4-wire representation, and you can apply that to low voltage networks as well, including neutral displacement, multiple earthings, and so on. So just think about, once the estimation has run, it is almost as if you had measured everything throughout the network. It just maps the available data and measurements into virtual measurements of any operational parameter you could possibly measure. In RMS though, right? So we can't do, if you want to do fault detection or so, then state estimation results are no good, but if it's just under normal operational conditions, it is as if you had measured everything. And immediate use cases that you could built on top of the estimation as well. For example, just regular asset performance. Just have a look at how hard you're running the transformers, what is the actual most likely loading of your lines. This already allows you to kind of infer, is there more space, more capacity on that network, on that feeder? And even just, you could even think of feeding those results, because you get, if you feed a time series of your measurements, you get time series of all your assets. Through thermal models, for example, to predict the aging of transformers. So virtually you have an asset performance information for everything that was in that network. And you can also run a kind of a compliance test. You can evaluate where in your network you might be outside the statutory limits, and kind of calculate the statistical distribution of it. As I said, the engine underneath within this project is a 4-wire implementation, so you get full 3-phase and neutral displacement, which in low voltage network, on MV level not so much, but in low voltage networks, that's extremely important, because the neutral can be quite shifted if you have unbalanced conditions. One thing that is a bit different, I still want to mention it, to power flow analysis in state estimation, if you have a bit of spare measurements, a bit more than you actually really need, you can start looking for errors. And you can, so if you have, mathematically speaking, if you have a bit of measurement redundancy, you can start looking for measurement, model errors, both in parameters and topology. And especially in the case of Energix, where we had downstream LV measurements of 30% of the distribution transformers, we were able to correct things like phasing and detect wrong tap positions and these kind of things. And as measurements further down in the LV get more available, probably soon from customers, I'd reckon, these kind of functions, the quality and problems that we see in the LV networks, network models, to some extent, you can actually use state estimation to guide you where the models, where the errors are. I wouldn't go as far yet as saying, okay, let's automate that, because to really robustly automate that, you need a fair amount of redundancy. I wouldn't say we're going to be there anytime soon. The way we've implemented it is we built a complete standalone system. I spare you the internal functional diagram, but it's a parallelized system, so we wanted to be prepared for possible rollout. So it is a central coordinating unit that coordinates a set of servers, and you define how many. So in case you run out of processing power, you just throw in more servers. It's generally web-based, so multi-user, multi-session, all that, and you can also use the web APIs to connect it to your own internal IT systems if you want to take control of it, not just to exchange data, but to take control of it. The one extension that we're probably going to see in this relatively soon is we kind of, with this project, reached into the down to the LV side of the distribution transformers. That, and many people have come up, as I mentioned, that as being one of the most crucial ones, is LV state estimation. And this is probably where I also have a couple of interesting insights for you. But quickly wrapping up on the MV, the experience from what we've seen is that in all three cases, especially the voltage profile throughout the MV and down to the LV side, was pretty much bang on. So we on the LV side of the distribution transformers, even in the case of test networks, where we had in some locations temporary loggers and we could compare, we were usually within 1.5 volts, even at the most remote point. And mind you, the bridge water feeder with something like 350 or 360 transformers from memory, many of them single phase, but I'll say we only had 8 measurement points in total. So especially the voltage profile is reasonably easy to estimate. And as you start increasing the number of measurement points that you make available, usually what you see is then as the second operational parameter that converges is the flows towards the upstream network, which is mother math at her most kindest, I would say. Because in this case, these are the two parameters that we're most worried about in terms of limiting the capacity of network. The feeder further down, the voltages further down in the network, plus the flows that are by tendency the most extreme towards the infit. And exactly these two parameters are the ones that get more precise the earliest. And in this sense, the project delivered on its original mission. Saying, okay, all 3 DNSPs that we worked with had enough data and it is functional. What we did in a project alongside, which we're definitely going to include in the near future, not within this project, but in the continuation of this work, which also used the same engine, or let's say an ancient version of that engine, that's the state estimation engine, was a low voltage network trial. And this is where it probably gets really, really interesting. Because most of the troubles for regular customers obviously are on the LV. Somehow understanding of what's happening in the LV will be required. So with the help of our incredibly supportive Energy Queensland, partners at Energy Queensland, we've set up a low voltage state estimation trial in Mitchelton, which is not too far from here actually. We tortured that network a little bit and installed so many different things. The customers actually came out and just were wondering if they did anything wrong and were being investigated. So that network would, as many of the low voltage networks at Energix, have a transformer monitor just here. This is where the infeed is. We've placed 3 additional smart meters with Rogowski coils in this case. So it was part of a kind of a combined technology trial, I guess. So one more here into the spur, one into this one here. For good measure, there was also a StatCom installed, a 3-phase StatCom. And while we're at it, we installed also 34 measurement devices on a customer level, but with customer consent. So the whole network supplies, I think, 106 or 109 customers, most of them single phase. So it's a pretty comprehensive test bed that we were able to work with. The interesting thing was the estimation itself was already functional just off the transformer monitor. That already, together with the customer counts at each pole, was enough to solve. For the network itself, we didn't really know or didn't really have network models. We only had kind of information like 15 meters moon, like just like the typical asset information. And we didn't know the phasing of the customers. Only for the ones where measurements have been placed, we actually knew later on, we knew what the phasing was. So we had to kind of associate each customer with a virtual 3-phase unbalanced connection. But the voltage profile throughout the entire network was, again, pretty okay. Running on the transformer plus the 3 additional smart meters that have been installed brought us to about 1.5 volts maximum error at the end of the runs, which is not too bad, given that you have 106 or 109 customers and you're effectively running off 6 measurement points. So as for the MV state estimation, it reveals all the operational parameters in it, sure, with a hefty uncertainty when it comes to the behavior of individual customers and the flows, especially towards the end of the network, because we exploit or we assume that customers have a certain similarity in their behavior, so highly correlated behavior. Some might argue from a privacy perspective that's probably good that we can't figure out what an individual customer is doing, but for voltage values and also the flows towards the in-feed, the results were pretty good. That scenario with the 4 smart meters is probably not the most realistic one. It was interesting because we kind of that was the first one that we got to work. The more interesting one is using the customer side or premise level measurements that we got available later, because they are kind of an example, a possible example of externally sourced information. While I don't see DNSPs installing smart meters and flow measurement devices into multiple ones into all of their LV networks, I can imagine them starting to purchase or retrieve or by any other means just getting premise level data from customers, from the home energy management systems, from the PV inverters, voltage readings, for example. So that is the most likely scenario. This is a reasonably complex visualization, but there's an interesting message in it. So give me a tiny moment. So that's a summary of the voltage estimate precision within that network. So what you're looking at here is you see these numbers up to 34, also down here. These are the 34 customers where we had premise level measurements. Okay, so that corresponds to the customers with measurements. So both the first 34 columns and rows. The overhang here are the additional measurement devices that we had still installed, plus temporary loggers. The scenario that we wanted to run here was, given that you have either a measurement on the transformer or a result from the medium voltage state estimation, what's the value of using customer level or premise level measurements, and how does it improve the estimation quality? Primarily targeting the voltage profile, because the voltage is probably the most pressing issue at the moment. So what you see here is, so the individual columns line up also display the differences between the actually measured voltage value and the estimated voltage value, while the rows correspond to different scenarios of what we provided into the estimator. So we varied how many of the available measurements we actually put into the estimator to then see what is the impact on the precision. So the first row would be 0, that is only running off the transformer monitor, nothing else, so no premise level voltage measurements. And then indicating the differences between the actually measured voltages and the estimated voltage throughout the rest of the network where we had measurements available. And it's a fair share of the of the customers that we have. Red would indicate 5 volts difference, yellow 1 volt, green is spot on 0. So what we did then is we added one after another the available premise level measurements into the estimation to kind of simulate we had access to it and see what the impact on the precision is. So this explains this diagonal black line. Everything below the diagonal black line means that value has been included into the estimation. Everything on the right side has not been included into the estimation, so it's a true estimation result where we had measurements available to compare to. This is why this is generally a bit more greenish and yellowish. But the key thing here is, first of all, it's functional on all of these different densities, measurement densities. It was operational just off the first measurement available from the transformer, which ultimately might come from an MV estimation. You might not even have a measurement there. Sorry. But the thing is, it looks a bit like matrix-like, the visualization. The really interesting part is how quickly it more or less converges. So this network supplying 106 or 109 customers, a bit more than 100. If you go out here and have 19, 20 measurements, that's about 20% coverage of premise level. And then you have next to 0 marginal improvement on the estimate. So if the only thing you're really after is the voltage profile of the LV network, you probably saturate at 15 to 20%. There's no point in going 100%. And that's a similar pattern that we also saw on the MV level when working with Energix, where we have the load points measured, so the distribution transformers. Also there, at about 20%, the voltage profile sells, and about 30-40%, the flows towards the infeed start settling. So this is probably where these tests have been are quite informative and quite relevant, because it's really, you don't need to measure everything. And these locations where the measurements have been installed have been selected randomly, effectively, because we had to ask the customers to consent, and not everybody did. So it's a robust process that can ingest that. We can quantify the uncertainty in it, and you don't really need to have 100% coverage. Last comment towards what we've built on top of that and towards the envelopes. Once you have a state estimation, you have a lot of building blocks for automated network analysis. Think of it, a power flow analysis is a special case of a state estimation process. State estimation can use an arbitrary set of inputs, measurements, while power flow analysis just does the same thing, but forces you to specify certain values. So if the moment you have a state estimation engine, you can build a power flow analysis straight away. You have the network model, you have all the mathematics implemented. So what we've implemented there as well is what we termed post-estimation processes, where we would use the method we've implemented to reinstantiate the network model, provide the estimated system state as a starting point, and then offer the mathematical components that you would need for network analysis. So you can build you can build Newton-Raphson-based analysis. That's what we did for PV connection assessments, where we simulated an additional PV on top of the estimated system state. So what would have been the likely system response to a PV system in the past if it had been there? So these kind of functionalities can be implemented relatively quickly and also run in parallel on the system. What I'm really what I personally am really interested in is full network abstraction. So I don't have that much time to go into it, but this is what I would say the operation envelopes are, and capacity constraint systems ultimately are. These are representations of the network and network capacity in a form that doesn't require you to know it is even a network. So there's going to be a lot of things, a lot of magic that's going to come out of that. So we basically built a platform to kind of automate these kind of network analysis and ultimately derive value, because the estimator provides knowledge. Knowledge has a static value. It's only once you can translate that into better decisions that you ultimately make, that create value. And this is where we can automate these processes. Okay, so yeah, summary for that. All of the 3 DNSPs, and I think they're reasonably representative of what's out there throughout Australia, at least on the MV level. had enough data to perform state estimation. The quality actually surprised us a lot, especially when it comes to voltages. And it's currently, the SCI system is currently available on MV, will be extended to LV. And it's a parallelized system that can ingest time series data for processing looking backwards. But we also have a real-time deployment at Energix that sits in their operational environment. And it allows the implementation of quite a range of different analysis tasks and automate them within the system. Yeah, thanks a lot for having the opportunity, or giving me the opportunity to present today. I'm extremely proud of this project. And you're going to see us around for longer, although the project concludes at the 5th of December. It's now being commercialized in a company called GridCube. And if anybody wants to know why we called it Cube, what the thing about the Cube is, happy to tell you all about it. And thanks for your attention. Thanks for your time.